Here we're being asked about the convergence of this infinite series, the sum n equals 1 to infinity of n over e to the n squared. And so the main approach to all these convergence problems is, first of all, to decide what test might be most applicable. Let's run through our list real quick, and we'll start excluding some, and then when we have our list whittled down, then we'll talk about the remaining ones a little bit closer. I think it's pretty clear it's not going to be the nth term test, because as n gets larger, this guy definitely goes to 0, because e to the x vastly outraces x to infinity. So the denominator is going to get much smaller, or much larger than the numerator, and the whole fraction is going to get much smaller. So because our terms go to 0, then the nth term test isn't very applicable. It might still converge or it might diverge. It kind of depends on how fast the terms go to 0. So that's not really going to work. The integral test was definitely a possibility. If this was a function of x, if we had f of x equals x over e to the x squared, which you could rewrite as x e to the negative x squared. This is actually a strong candidate, because this guy is integrable. It's u substitution e to the u du. So I'm going to keep that high on the priority list, but let's keep looking to see if there's anybody easier. But that's definitely a strong candidate for how we might solve this one. Direct comparison, limit comparison test, I'm not really seeing too much here. Who would you compare them to? There's not really anybody good, larger or smaller, that converges nicely. So I don't really see us using either the comparison test here. It's definitely not a p-series. Doesn't look anything remotely like a p-series. Alternating series test, of course not. Nothing alternates. All these terms are positive. For alternating series, you expect to see -1 to the n or some version of that, so that it flip-flops plus minus, etc. Okay, so definitely not that one. The root test, definitely not. There's no powers of n, or at least this numerator doesn't have a power of n. It's just n. So I don't really see that being the root test either. The ratio test, again, I mean, if you took the n's out and put n plus 1s in its place and did proceeded with the ratio test, which I assume that we know. If you're not familiar actually with any of these tests, we have individual videos on all of these. So I'm assuming that we're very familiar with all these. I don't see the ratio test being very practical either. So actually this one, it basically answered itself. It looks like we're going to do the integral test for this guy. And so when you work problems, I encourage you to use the same approach. Think about all of your tests, and then just start excluding ones that don't seem practical, and then examine a little closer the remaining ones that do seem like a possible choice. So let's see here. Let's write his equivalent continuous function. It would be x e to the negative x squared. And the integral test said that if you can take an integral from 1 to infinity, like the series is from 1 to infinity, of x e to the negative x squared dx, because these functions match at every integer value, because they're the same, this is just the continuous version of this guy right here, then if this guy converges, then so does he, or if this guy diverges, then so does he. But they're inextricably linked together, and so because we can compute this, we'll find his convergence, and then based off of that convergence, then we can talk about this guy's convergence. Okay, so I think we know what we need to do here. All right, so for improper integrals, what we do is, rather than integrate from 1 to infinity, you can't use the fundamental theorem of calculus for that. We'll integrate from 1 up to what we call b or a or c, or pick a letter, x e to the negative x squared dx. Then after the integration is completed, since we only went up to b, we'll take the limit as b pushes its way on out the rest of the way to infinity. Okay, just to save a little time, I think you guys can compute this integration here. It's not too terribly tough. you get negative 1/2 e to the negative x squared. You're welcome to check my algebra on that. Bracket from 1 to b with the limit as b goes to infinity. Alright, we'll plug in a b and we'll plug in a 1. We'll subtract. So we have the limit as b goes to infinity. If you plug in a b, you get negative 1 over 2 e to the b squared. And notice all I did was I put the negative exponent back in the denominator. That's all I did. Okay, minus a negative makes a plus. And then you get 1 over 2e, basically. All right. Now you let this guy run on the way, the rest of the way to infinity. Let b get larger and larger and larger. Should be pretty clear. That term goes to 0, right? It goes to 0. So this goes to 1 over 2e. That's a finite value, meaning that this improper integral converged. So this guy converges, right? Now remember integral tests. What did the integral test say? It says that if your improper integral converges, then handcuffed to it is this infinite series, and because since he converged, then so does he also. So this infinite series converges, he converges by the integral test. Okay, so that's how it works. Now, one comment I'll make before I let you go. A student might misunderstand this 1 over 2e. That's not saying that this series adds up to 1 over 2e. Yes, it converges, but I still don't know who he converges to. But I know that these guys either converge together or diverge together, and the improper integral converged to 1 over 2e, but that doesn't necessarily mean that the infinite series converged to 1 over 2e. I know it converged, but I still don't know exactly what it converged to.